Hi guys, we're back to talk more about plates and plate tectonics, and this time we're going to talk about some of the functional differences between parts of plates that are made of oceanic material as opposed to continental material. So I'm going to share my screen so that we can see this, and we'll start from the beginning here. Okay, so there's a term that we're going to get into called isostatic equilibrium, and isostatic equilibrium refers to the equilibrium position that something will end up sitting in or occupying when the forces pushing down on them and the forces pushing up on them are balanced. And so that's kind of, you can imagine where if you throw something in the water, it might bounce into the water and then it'll kind of pop back up and bob around a little bit until it finds a position where it's going to be at rest. The same thing happens for lithospheric plates. And so we're going to think about the differences between what happens in the oceanic pieces and the continental pieces. So we'll start out with the oceanic pieces. They are relatively thinner. The crust, the upper part, is about 5 to 10 kilometers thick. They're primarily made up of a rock called basalt, which is a darker colored rock. If you look at this picture over here, you can see underneath the water in the oceans, there's this dark black volcanic rock. It's an igneous rock, which means it's formed from volcanic features, and it's extrusive, which means it forms outside the earth as lava erupts onto the surface. And it's also mafic, meaning it's rich in metals like iron and magnesium, which are heavier elements compared to things like oxygen or aluminum that comprise a lot of other rocks. And so it is a relatively heavy or dense rock compared to a lot of the rocks that we see on the continents. We also mentioned before that the average age of the rocks underneath the ocean is quite a bit younger. They're constantly being recycled. So the oldest rocks are only going to get up to 180 million years old, which is relatively quite young. So this is different than moving over here to the rocks that form on the continents. Right? And you can see this big thick piece is a lot thicker than this little black piece that is allowing the ocean to sit on top of it. So these continental rocks and the crust is a lot thicker, 20 to 75 kilometers thick. It's made primarily of a rock called granite that you would probably recognize from its classic salt and pepper-ish look. It is an intrusive igneous rock, so also forms from volcanic features, but intrusive means in the inside of the earth. So cools down in magma chambers and never erupts onto the surface. And it is considered a felsic rock. And these rocks are usually lighter in color and a lot lower in density, so relatively less heavy compared to basaltic rocks. And rocks on the continent can vary in age quite a bit. We have, brand new rocks that have formed around volcanoes in the last week, but we have also some very old rocks that are over 4 billion years old. And a lot of the basements, the foundational pieces of our continents are many billions of years old. And so on average, these rocks are much, much older than those rocks that are constantly recycling underneath the ocean. Okay, so these differences in both density, relative weight, and thickness are important because they will affect the isostatic equilibrium position that ends up being achieved by the two different kinds of material. So as I mentioned before, something's isostatic equilibrium, or kind of its isostasy, has to do with what forces are pushing down on something, and the forces that are pushing down on things have to do with gravity. And so the more mass that you have, or the denser you have material packed together in a space, the greater that downward push is going to be. And then if that object is sitting over a fluid, which the lithosphere is sitting above the asthenosphere, which is only a little bit melted, but acts a little bit like a fluid because it can move. Fluids push up on things in proportion to the volume that object is sticking down into the fluid. So not so much about the weight, but more about the volume. And so practically what that means is the way that or the position that a certain object is going to achieve above a fluid is going to be influenced by, first of all, its density, how much mass is packed into that material, and then also by its thickness, which, you know, how deep it is has to do with its volume. So first of all, if two things are the same size, like a dense piece of mahogany wood as opposed to a piece of cherry wood, this mahogany wood is 0.7 grams per cubic centimeter versus cherry, which is 0.4 grams per cubic centimeter, and they're the same thickness, we would expect the denser piece to sink lower than the cherry piece. So we mentioned that there's two rocks, basalt and granite, and that basalt is denser. So if they were the same dimensions, we would expect already that the basalt would be sticking down a little bit lower into the asthenosphere relative to granite. However, there's another component which has to do with the thickness or the depth of these rocks, or in some of the pictures here, boards. And so in this case, what happens is how thick you are or how deep you are is going to affect the volume of fluid that you're displacing, and that's going to influence how much push you're getting from below. So in this example over here on the right, we have a bunch of blocks that are supposed to represent all the same kind of wood, so all things that are the same density. And so in this case, in each block, about the same proportion of the block is below the water as opposed to above the water. So maybe it's 70% below and 30% above. But blocks of different thicknesses are going to then stick deeper distances down into the fluid below and stick different distances up into the air depending on how thick they are. So this block and this block are both sticking down 70% and up 30%, but the 30% up here is like a mountain, and the 70% down here is sticking way farther down into the fluid. So if we wanted to have things that were all lined up, we would have to have denser materials that were thinner, medium density materials that were a little bit thicker, low density materials that would be floating higher up above the fluid, but a lot thicker, and then we could create some interesting stair-step pattern like this based on the different isostatic equilibriums of this highly dense, intermediately dense, and low density materials. So the oceanic pieces are thin and dense, so they're going to be riding low in the water or in the asthenosphere, but they're relatively thin. And then the continental pieces are less dense, so there's going to be a higher proportion of that rock sticking up above the asthenosphere, but because it's a lot thicker, it's going to end up sticking both higher up and a little bit deeper down into the asthenosphere. Okay, so what does that look like? Well, we have a thicker piece here, a thinner piece here, and we can see that this thin piece is actually not right perfectly in the middle of this thicker continental piece. That's because it's a little bit denser, so it's sitting a little bit lower. But even so, this big, thick continental piece is probably going to be extending a little bit below the bottom of the oceanic piece here, and it's definitely going to be sticking considerably up above, and that's because its density is quite a bit lower. The average density of a rock like granite is about 2.7 grams per cubic centimeter, whereas the average density of a rock like basalt is almost 3 grams per cubic centimeter, and then both of those are less dense than the rocks below that have an even higher density down in the mantle, like peridotite, and certainly much lower density than the metals that we see in the core. Okay, that's a good stopping point that will allow us to understand plate behavior along plate boundaries, which is our next topic.